So welcome to the 11th class of data analytics. We've been going through interactive visualization, probabilistic modeling, and the last, which is really the big module, is machine learning, right? And last week, we kind of finished with supervised machine learning. Okay, so if you will recall, again, this is my theme here. Data analytics is about asking this and then asking this. Right? Okay. So again, talk about visualization. The first question would be, where are the data? This would be, visualizing using histogram, right? And when you move to probability and statistics, then you start to do some kind of summary statistics like X bar and S. And ultimately, you start to model the distribution, right, where things are. So this is one distribution, and that would be maybe the mean, this is standard deviation, whatnot, okay? And likewise, if we're talking about the second line of question, which is, if I knew X, do I know Y? Can I make a good prediction of Y? And again, for visualization, maybe you would rely on some kind of scatter plot, right? For probability and statistic, then you start to think about trying to estimate regression coefficient, right? Something like that. Okay. Right. And then essentially you try to create some kind of a model, right? And so for the last 2 weeks, for the past 2 weeks, we kind of like been addressing this bottom right here, right? Which is a machine learning, supervised learning. Okay, supervised learning, right? And there are two major types. One is kind of like a tree-like, and that kind of like mirrors abstraction of a human logic, right? And the other one is more like neuron-like. That's basically artificial neural network, right? That's separating by kind of like the style of the methodology. But you can also, we also study that there are actually two types of problems, right? So one is a classification problem, which again, to your biologist friend, is identification problem. So you are given some data that has label. You're supposed to learn that. And so when you see the next example that you haven't seen, you can correctly identify, yes, it's a cat, it's a dog, it's an apple, it's an orange, right? So that kind of labeling, right? Classification. Or if it's a human face, it's a happy face, it's unhappy face, whatever, okay? And this goes all the way up to, text model like sentiment analysis. There's a sentence and you say, oh, this is a positive sentence. This is a positive review of a restaurant, positive review of a movie, negative review of a restaurant, negative review of a movie, whatever, okay? And then there's more numerical. Why is numerical, right? That's sort of like, sometimes you call it forecast, sometimes you call it basically the regression kind of problem, but we would call it prediction, okay? And how do you build those? Well, you build classifier using classify function built in Mathematica. You use, how do you build predictor? You use the word predict as a built-in function, okay? Now, so today, the topic of today is to come up here. Unsupervised learning, right? Unsupervised learning, okay? So, right. Okay. First of all, let me go back a little bit to probability and statistics. The reason I want to do that is because I want to mention another problem in probability and statistics that wasn't addressed much. So let's say I have a histogram that looks kind of like this. Okay, right? Histogram that looks like this. So what's my job? My job is to fit like a distribution, correct? Distribution. Okay, right? And we can do this in 2-dimension, 3-dimension, and whatnot. Okay, and again, you can do it with Mathematica. You can use this thing, find distribution. Right? Right? Find distribution, right? Now, this is actually a very powerful way of doing things already, but to align with what your friends may be doing at the statistical department, just want to give the narrative, okay, where how rigorous or how much of a pain it would have been if you were doing it the old statistical way. For example, you have to test, does it have a symmetric kind of like right side, left side? Does it have a heavy end? If not, blah, 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 then you think it's a normal distribution. So basically your job it's not that easy, right? It's not that easy. Your job is actually to have in mind what the distribution is. For example, normal, gamma, exponential, beta. You have to have the brand name first, right? And then you ask the computer, like statistical library, like I think RView or something. There's this stat view or something like that. Ask it to come up with the parameter. So basically, life is not that simple. Okay, in your statistical friends class, what they would actually have to do is have in mind, okay, I'm going to use distribution is equal to normal. And because distribution is a normal, I have three parameters to estimate mu and then sigma. Okay, so I have to do this. Okay, right? Likewise, if your distribution is equal to, say, gamma, then you have a parameter, something like, I think it's called alpha and beta. What is it? For example. Okay. And if you have, let's say, Poisson, then the name of your parameter is this. Okay. And then you have to use the data to estimate this guy. Estimate this, estimate this, estimate this, estimate that. Right? So in Mathematica, you also have that. That would be something called, I think something like find distribution parameter or something like that. Okay, parameter. Okay. Now, by the way, this is rarely ever done in life because most people who would do statistics, they have in mind what kind of probability distribution it is. In fact, there's a limitation that find distribution only work for one-dimensional data. Okay, for two-dimensional distribution, you have to do something like this. For example, bivariate normal, and then you find the parameter. Okay, that's a side note. Anyway, the point I'm trying to say is, here, you don't even know what the distribution is, and you ask Mathematica to come up with it. That's kind of like a cheat code. That's kind of like a hack. Okay, so that uses computational search. But if you were to do it in traditional, if I were to teach you like a traditional statistical class, I would have to sort of like, guide you to, okay, this looks like a gamma because it's positive, it's continuous, and it's got this kind of shape. Or if it's bounded between 0 and 1, then it's probably beta and that sort of thing. So there's like a rule that you follow, so to speak, to diagnose what distribution is before you get to the stage where you can estimate the parameter. Okay, so that's the story with probability statistics. Now, one thing that I did not mention in probability statistics is that if you look at all the distribution that we study, okay, it's going to have very simple shape. Simple shape. More importantly, I'm going to use the word it's going to be mostly unimodal. Okay, what's the word mode? From lecture 2, I think. Mode is the most frequent, right? So if you're talking about a continuous distribution, the mode basically is the peak of the distribution. What does unimodal means? Means one mode, i.e., if you plot the distribution function, it has at most one peak. Okay, so this is one peak. Normal distribution is one peak. Gamma distribution is one peak, right? A special case of exponential function. Well, this one, you can call it peak, but it's actually infinite. Okay. So technically, mathematically, they don't want to call it peak. They call it kind of like convergence. But anyway, it's only when you look at beta distribution. Actually, you might do it right now if you want. Go to Wikipedia page for beta distribution. Remember, beta distribution is bounded between 0 and 1. It can have this shape, right? It can also have this shape, but it can also have this shape, and more interestingly, it can have kind of like bimodal shape as well. Okay? Fine. Still, my point is that the idea of distribution fit is that there's only one population. Okay, there's only one population. There's only one population. That's what I want. Okay, there's only one population. So inherently, you make an assumption that you're trying to fit the distribution to this population. Right? That's the idea. That's the idea. Now, in real life, two things can happen. Okay? Two things can happen. Now, I'm going to use human height as an example. Okay? I'm going to use human height as an example. Let's say you take human height, and the best histogram you can come up with looks like this. It's got kind of like two modes, two peaks, right? Doesn't have to have the same height. It can be one can be higher than the other. Okay. Let's say you ran into this in a situation. Okay. Now, what follows depend on your assumption. Your assumption is this is one population. It just happened to have two peaks. That's one thing. Okay. The other is you can make the following statement. You can say, actually, what you're looking at is a sampling of two distributions superimposed. Does that make sense? Does that make sense? So if number one, case one population, two modes. Okay. Now, if I can do two modes, I can also do three modes. Okay. So 2 plus mode. Okay. Right. Okay. So that's the assumption is you're trying to fit one distribution, but somehow that distribution happens to look like this. Now, if it's between 0 and 1, maybe you have a choice to fit it with beta distribution. Okay, but this one beta doesn't work, right? Because human height is positive, it's not between 0 and 1. So here's the thing. Here's a trick. Not a trick, but technique. If you are going to get this, how about, and all you have are like this. Okay. How about this? How about you have what's called a mixture? Okay. For example, you can have this one, oops, sorry, and then this one added together. Does that make sense? Does that make sense? So basically, I draw one PDF, I draw another PDF. Now, each PDF has an area of what? 1, right? So if I add to PDF, is that going to be a PDF? No, of course not, because it's going to have an area of 2. So basically, I have to scale down. For example, 50-50. Okay, so an example would be, okay, for example, this distribution is equal to 50% normal mu 1 sigma 1 square plus 50% normal mu 2 sigma 2 square or sigma 2. Does this make sense? Right? So for example, let's say this is 0 and 1. So I have this one, 0 and 1. Now this is not human height because human height is not negative, right? And let's say this one is 2 and 3. Okay, what's going to happen? I'm going to have another line that looks kind of like this to the right, right? Right? So this one comes from here. This one comes from there. Let's say it's 2, 3, say something like that. So it's to the right and it's wider spread. Can I do that? Yes. Now, to add them, I have to scale this down so that the total area adds up to 1, right? So I make 50% of this and 50% of that. Now, obviously, 2 things can happen. You're smart. You see where I'm going with this. First of all, why 2? Why not 3? Right? So I can have 3 normal distribution. So I can have more complexity. Second, does the weight have to be 50-50? No, it doesn't. It could be 70-30, right? So this becomes a free parameter, right? 2. Okay? If I did all this extension, it's called Gaussian mixture model. Mix because you have this. Gaussian because this is a Gaussian shape. However, if you're smarter still, you would guess what I'm going to say next. Why limit to Gaussian, right? So a mixture model can be gamma and gamma. More than that, it can be gamma and normal, right? And exponential. You can do all kind of stuff, basically. Okay. So once you treat this as a sort of like a free for all, you know, just throw everything at it. Now, this I would call it semi-parametric approach. Parametric approach means you have a distribution in mind. Again, you're not asking Mathematica to say, find me a distribution. You have a distribution in mind, but you're asking Mathematica to find the parameter estimate, the estimation of the value of the parameter, right? So that's parametric. But if you're doing this kind of thing, you know, you really don't have a clue that it's normal or not. You're just kind of like trying, okay? See which one sticks. So maybe 2 nodes, you try 2 normal. Maybe you try 2 gamma. Maybe you try 1 normal, 1 gamma. Maybe 1 normal, 1 gamma, and another one is log normal. I don't, you know, all kind of stuff. So this kind of open-ended search, it's like you don't have a model in mind. Sometimes we will put this under semi-parametric. Okay, so this is really an extension of going back to the prop fitting. Okay, now why am I mentioning this today? Why am I mentioning this today? Actually, I could have mentioned it back then, but then I would have to, you know, go back and talk about it. Okay, in this case, fundamentally, your belief is that there's one population, but to model the distribution, you need component distribution. Okay, so you get like a mixture, right? And by the way, you can do this. So basically, you make this a parameter, you make this a parameter, you make this a parameter, you make this a parameter. For example, you can call this P, and this one become 1 minus P, right? And then ask Mathematica to come up with it. Fine. By the way, if it's for 2-dimensional up, you need to do this way. You can't do fine distribution. Fine distribution is very kind of like a quick hack. It only works for 1 dimension. Okay. For 2 dimension, you have to do this. Fine. So that's what you would have to do if you were doing a statistics proper. Now imagine, okay? the world where you have this kind of model is very limited. The world where you have this kind of model is limited. So you want to search kind of like the flavor that I was heading to, you know, instead of having one component, have two components. Instead of having two components of the same type, have two components of different type. So you're just trying to find all kind of stuff. If you want to operate in that world, chances are you are moving toward unsupervised learning. It's kind of like a signal, right? When you run into this kind of situation, you almost kind of thinking, you know what, maybe it's about time I leave traditional probability and statistics and go to unsupervised learning, okay? Which is what I'm going to start with today. Now, there is a distinctly different thinking. It's not necessarily that you adopt this kind of distinction, but you can see that this kind of mixture approach, you kind of have this implicit statement guarantee that it's actually same population, just based on two components. Now, let me flip your mind around and say, hey, what if okay, instead of having one distribution that kind of looks like this, and in order to model it, you model it as this plus this, okay? And some percentage P of this and 1 minus P of that. Instead of that, what if, okay? I distinctly whisper to your ears that actually, you know what? There's a good reason why there are two humps. They're two different kind of people. Aha. Okay. So it's actually two different kind of people. Okay. It's very different now, right? Previously it was technical. So basically, previously I have D is equal to P1 D1 plus 1 minus P1 D2, right? Because these add up to 1, okay? Because it's a technical requirement, right? I'm trying to fit the data and I can't fit two humps with one distribution. So I use two distributions to fit. But now I'm saying differently. I'm saying, hey, you know what? Actually, the reason you saw that is because I have gathered the height of 5,000 women and 4,000 men. Okay, 5,000, okay, 4,000 men. So in that ratio, so let's say this is I can't think of any situation, but let's imagine this ratio is fixed, okay? So in that case, you would have something like this distribution is equal to 5/9 of D1 girl plus 4/9 the boys, right? And this is the people. D stands for distribution. Does this make sense here? Right? So it's a different from before. Before was a technical need. I need to find two hum. I don't know what to do, so I'm just going to make take two component distribution and add them kind of ad hoc. But now the model is different. Okay. The thing is, you would use exactly the same technique, right? Use a mixture model. Okay. So you can do that. Okay. Does that make sense? Now, what I'm trying to say is when you go to unsupervised learning, the focus tends to be on the difference of subpopulation. Okay. In statistics, you're trying to model a population. Occasionally, you have two humps, so you need two distributions to add them together. Occasionally, somebody will whisper to your ear that it's actually because you see two nodes. There's a good reason why, because you're actually adding two subpopulations. Okay, that's very occasional thing, right? Most of the time, it's one distribution. what I need you to understand is that when you go to unsupervised learning, not only is the data more general shape, but you are also more focused on segmenting the population. So in other words, this thing for traditional statistic is asking a question, where data at? Yeah, where data at? Okay, where are they? Where are they? That's traditional statistics, right? Whereas in what we are going to do today, which is unsupervised learning, the question would be, hey, subtype. Can you partition into subtypes? Okay. Now, get your mind to think commercial. Get your mind to commercial. Okay? Again, you're trying to sell t-shirts, and t-shirt has a size of height, right? If you can model where the data at, then that gives you a distribution of size, right? So you can say, well, you know, I'm going to make 1,000 t-shirt. I'll make 200 small, 300 medium, 400 large, and 100 extra large. Okay, that's your thing, right? So it's kind of like partitioning along this kind of fixed dimension. However, for this kind of question, it's a little bit different. It's more subtle. It's something like, hey, I'm going to make t-shirt for different lifestyle. Can I separate the population of one population into subtype? So there's like, you know, I'm going to make t-shirts. So this is not about size anymore. Still one size, but I'm going to make like 300 t-shirts. That's for urban type, right? I make 100 t-shirts for the nerdy type. 200 t-shirt for the, you know, cutesy Hello Kitty type. Okay, that sort of thing. Okay, so this is about trying to partition, right? Trying to partition the subpopulation. And you can see why this is very popular in modern marketing, right? So you can, historically, this is not what happened, but you can think of this analogy and hope this analogy stick with you for the rest of your life, right? Back then, you're making a white t-shirt. You just need to know how many small, how many medium, how many large, right? So you have this kind of like quantitative distribution over size. That's the deal, right? But now you are design conscious. The t-shirt is actually free size, but kind of different style, right? One caters to the urban consumer, one, you know, cater to the rough and tumble, one cater to the very, you know, cute anime kind of thing. I don't know. Okay. So in that case, you're not trying to separate, you're not trying to find the quantitative distribution of size, right? But you're actually trying to uncover the hidden label. Now think about it, guys. What did I say before in the previous two classes about classification problem? You have predefined labels, cats and dogs, right? Now imagine it's not real cat, it's not real dog, all people. But I'm going to separate lifestyle. So maybe there is a cat people style, there's a dog people style, and dog people and cat people buy things differently, right? There's a Game Boy people, there's you know, nature loving outdoors kind of person, and there's indoor cats and outdoor cats and indoor dog, tiny dogs in a basket. So these are all different flavor, all different consumer preference, right? So that's the world where we're heading at. Yeah. So in that case, are they so much interested in the actual mathematical shape of the the height or anything. No, they're just trying to partition, right? Right? Now think about it. Let me say that again. In the first case, because you need to quantify, how many small size, how many medium, how many, you need some kind of like a mathematical description of the distribution, right? But for the second case, let's say this distribution, I don't even know if it's normal, binomial, I don't care. All I know is that this is one type of the people, this is another type of people. And if I want to sell my t-shirt to this type, I have to draw a lot of kitties. I have to, if I want to sell t-shirt to this type, I have to draw puppies, okay? Your dog type. It's very different, right? Once again, if this were a classification problem, then I'm actually trying to classify cats from dogs. That's a real thing. That's a real thing, guys. A cat is born with the name cat. Dog is born with the name dog. I take the measurement, I take the whatever, and then I make the partition, I make the machine learn. This is a cat, this is a dog. But here, there's no such thing as cat people and dog people. These are artificial, right? However, maybe there is something that we can exploit. So inherently, there's a cat people, there's a dog people, okay? It's not a real label. It's not a real label. It's a label that I'm giving, okay? In fact, I don't have to say cat people, dog people. I can say people type 1, people type 2. Would that be okay? Yeah, that'd be okay, right? So the idea is that there's something about the attribute space, okay? So let's say this is height and this is weight. So there's a tall and heavy and tall and skinny and short and fat and short and skinny, whatever, that sort of thing. I don't need to have mathematical description of the distribution themselves. So I don't have to do what I did before with the D1, D2, D3, D4. I don't. All I have to do is learn the, and here's a key word, guys. Use this in exam. Partition. Yeah. Okay? Partition. Now, one more conceptual slides and we're done. This is a difference between what you did last week and what you're doing today. Both using the word partition. Yeah, notice that there's some kind of, it's not a perfect clean cut. Okay, now remember this picture. This is a difference between chapter 6 and chapter 5. They will both use the word partition. Here, the partition you're trying to learn is this line. Yeah, right? Because you are learning that this is the blue guys, that's the red guys. You're trying to learn that partitioning. Okay? You're trying to learn that partitioning. Now, in this case, again, this would be like cat people and dog people. It's not a real thing. However, because behaviorally, you can see that they're two different groups, right? Right? So I'm also trying to do the partition, except I'm not trying to make a general statement about partitioning cats and dogs. I'm just trying to keep two groups apart. So instead of using the word partitioning, I'm going to use the word clustering. One cluster, this is another cluster. Okay, so that's it. Take a picture of that. Well, I'll take a picture of that if you don't want to take a picture of that. Okay, so again, what chapter is that? Chapter 6. What chapter is that? Chapter 5. Okay. Now, why do I call this chapter supervised learning. And I call this chapter unsupervised learning because there's the right and wrong, right? So if I pick a data and I say it's red, but it's blue, it's an error, right? There's an output that the algorithm has to learn. So there is a cat and dog. There's a right and wrong answer. Okay? That's supervised learning, guys. Right? Whereas here, is there a right or wrong answer? Actually, no. There isn't. It's just my imagination is, I think this is one cluster of people. That's one cluster of people. Now, if I'm looking from a very far away distance, I can't tell teenagers apart. Actually, there's only one cluster called teenagers. Okay, but you guys know the difference between, this type of subculture in teenage lives that I'm not aware of, right? So it's not a real classification. It's not a real label. There's no right or wrong answer. If there's no right or wrong answer, can you algorithmically tell the computer, yes, this is correct. No, this is not correct. Can you? You can't. So how does machine learning operate if you don't give it a guidance of right or wrong? You give it some kind of criteria. For example, a good criteria would be if you organize this so that data that are close together belong to the same group. Okay? So how would you do that? Well, you give it some mathematical objective function like measuring the distance between you and your neighbor, say, right? And if people from the same group touch each other within arm's length, that's one group. Yeah? Does that make sense? Right? Again, this one has a right or wrong. So model output Y is equal to cat, but Y is actually equal to dog, you say it's wrong. Okay? So you give it a evaluation, right or wrong, supervised learning. In this case, there's no right or wrong, but there is a criteria for making the cluster. Does that make sense? Okay. This is sort of what problem we want to do. However, I'm going to tell you that this is only half of chapter 5. There's another half. Okay, I'll talk about it. Okay, but you understand now where we stand, right? Okay, so relative chapter 5 relative to chapter 6. Chapter 6 has label, has target, has Y. If Y is numerical, it's called prediction problem. If Y is categorical, like red and blue here, it is called classification problem. Okay, there is actually target to match. Okay, here there isn't. Okay, now vis-a-vis chapter probabilistic modeling, chapter 4, right? That chapter 4 is more about modeling the population, whereas this is more interested about separation. So this kind of gap is not something we did a lot in chapter 4, right? We don't care, okay? So now you understand where chapter 5 stands relative to chapter 6, relative to chapter 7. Oh, sorry. Where chapter 5 stands relative to chapter 6 and chapter 4. Okay, right. So you all clear on that? Yeah? Okay. Now we are going to go to technique. Okay, and I'm going to do hand drawing first, then I'll go to the real thing. Okay. Watch. Let's say, okay, let's do that data again. Okay. And let's make it more interesting. Instead of 2 clusters, I'm going to make it 3 clusters. Okay, so these are two problems. Now, conceptually, let's first agree that you can see this. So I'm going to ask you, does it make sense to do this? Kind of like cluster 1, cluster 2, cluster 3. Does that make sense to you? Okay. And this probably makes sense to you as well. Would you agree? Okay. Would you agree with that? Yeah. Would you agree? Okay. Right. Like I said, there's no color, red, white, and blue, and green. So there's no label. So you have to teach the algorithm, the unsupervised learning algorithm, the way it's kind of organizing principle. Things that are together belong to the same cluster. Okay? So this is X1, this is X2. Now, how would you tell the computer to make this 3 groups? Okay, let's say I tell the computer there are 3 groups. I tell the computer there are 3 groups. Okay, what exactly, like in supervised learning, you're minimizing the error. What are you minimizing here? Well, basically, if you belong to the cluster, this distance between you to the, let's say, center of a cluster, I'm going to make a little X here for center of a cluster. Right? Now, would you agree that for every point in this cluster, it's closest to this cluster center than it is to the other? Right? Would you agree? Okay. So that's the hint right there. This kind of clustering algorithm is based on distance, global distance. Okay. So I'm standing over here. It's like, it's almost like I don't have to do the clustering. I can ask individual point, hey, where do you feel you belong? Yeah, where do you feel you belong? Well, the center of this group is over here. The center of group that's over there, that center, well, it's almost like geography problem, isn't it? Right? Right? So I'm closer to this center, so I'll call myself cluster 1. That makes sense. That makes perfect sense, right? Well, that's exactly what happened here. The idea is you minimize the distance to your own center and you maximize distance from other center. Okay, that's it. However, I tricked you a little bit because I gave you the middle point, the axis, the red cross, where the center is. When you start, you only have data. You don't have the center point. So the algorithm actually works the other way around. You're not saying that this is a center point and ask the data, where do you belong? No. You actually say, where should I place the center so that you can gather center data around you such that you create this close, far for all the points that you will call. And if you did that, you call this part of you. So it's kind of like flip thinking, okay? Now, that middle part of that center, the cluster, the technical word for it is called centroid. It sounds like center, but it's not exactly center because it's not necessarily geometric. So basically, the algorithm here is to find the centroid. Okay? That centroid originally is random. And so the way the algorithm works, I'm not going to show you. It's like back propagation. You start out with some guess, and then you keep moving. Okay? So maybe in the beginning, the centroid start here, and here. Right? Okay? Now, let me describe the algorithm. This is what's called k-means algorithm. Okay? This is, okay, by the way, you can go to YouTube and just type in like how k-means work, and you see a lot more beautiful animation than I can do with my fingers. Okay, but basically you do this. You start with 3 points. You say which point is closest to this guy. Okay, okay. Consider that the cluster, working cluster. Calculate where the central part is. So take the average of the longitude and latitude and move it there. And just keep doing this, keep doing this. Okay. So eventually you end up there. That's called k-means. So this would work in this kind of like k-means, but there are many algorithms. K-means is one of them. I'm going to group this kind of thing as distance based algorithm. Okay, so it's based on distance, right? It's based on distance. So basically, how do you partition the population? You partition population by introducing the centroid such that the data belong to that cluster if it's closest to this centroid than it is to other centroid. Okay, so this is kind of like a geography kind of problem. Well, speaking of geography, okay, what if I take a satellite picture? Okay, I take a satellite picture at night. Take a satellite picture at night. Okay, and those dots are the lighted area. So what would you say? Well, that's where houses are, right? That's where the houses are. Okay, now what would be the intuition by, you know, why aren't houses like, you know, in a circle? Don't they like each other? Isn't it a close community? Why do you think that happens? Well, I'll whisper to you that these are actually 3 different villages. And then you ask them, how come villages are not organized in a you know, circle, in a radius? You take picture at night, you see this. Why? Well, it could be, for example, because it's kind of like a river here, right? Also, you can also have like a mountain there. That would be a good explanation, right? Does that make sense? Yeah, you take picture, satellite picture at night, you can't see. You just see this kind of banana shape, kind of weird, okay? If they're same village, why don't they gather together in a radio? Well, actually, they're actually doing this. This is one to the west side of the river. This is one to the east side of the river, but to the west of the mountain. This is one to the east of the mountain. Does this make sense here? Okay. Well, in this case, there's a hard and fast reason why, but let's forget about this. Let's just think of how can we come up with this boundary? Can you use the old criteria? You can't. Why does it not work here? Yeah, that's not, where is the centroid? Let's say, okay, for this guy, for example, the centroid, you know where the centroid of this guy is? In the middle of a river. Okay. So in fact, this guy is also so close to that centroid, so distance doesn't work. Actually, that's not true. Distance works except it's a contiguous distance. It's distance between you and your neighbor, right? So basically, as long as you can go to next door by reaching an arm, you are a neighbor. So imagine that I come in and here are students, and there's another student that does this, and there's a big pole, right? In which case there'll be this crescent shape, correct? Right? And that crescent shape, this guy is far away from that guy, but this guy can touch this guy, can touch this guy, can touch this guy, can touch this guy. So it's kind of like a dense, contiguous distance. We will call this density base. Density. Okay? Call it density base. Right? Now, unfortunately, well, not, let me tell you what unfortunately is. Fortunately, if you can look and see this picture, can you tell which technique works for which data set? Yes. Am I going to use distance-based clustering for here? No. Right? Am I going to use this density-based for here? Well, maybe you can, but don't need to. So it's, it's kind of like a judgment, but at least you can make a case. Now, if you can do this, you can partition your data. Well, the whole reason of using a computer is because you need to do heavy duty computation, right? Like estimate parameter. But I just told you, I don't care about estimating the shape of the distribution. I don't care. All I care is that I create this kind of circle around the data point. So why do I need a computer at all? The answer is I don't. Not for 2 dimensions. Problem is, just like your computer, all this platform trying to get information about you, they're not just taking 2 numbers from you. They're taking 50 numbers from you. So it is multi-dimensional, right? So everything I've said to you is true. Everything I told you is true. However, we wouldn't be studying this if you can see it. If you can see it, you can draw a circle around it. Okay? You cannot draw this boundary because in 20 dimension, there's also like a membrane in 20 dimension. You can't imagine, right? Okay? So that's why you need computer algorithm. In this case, by the way, you should always have this in the back of your mind. The reason we do everything with AI, machine learning, all of this, is because we want something that can do simple thing that we can do intuitively, except in 500 dimension with 2 million data points. It's always the case. It's always the case, guys. If you go down enough to the number of cases, okay, the AI is not going to know you better than your customer service if the customer service is only responsible for 5 clients, right? Nobody ever builds an AI to be a customer service representative if you only have 5 clients. You hire a human being for that, right? So it's always the case, guys. All thing about data analytics, AI, machine learning, probably the whole thing is that, yeah, you wanted to do human job, but humans cannot do it because it's dimension higher than 3 and the number of sample is greater than 7 or something. Okay? Have you heard that? There's like a magic number that human being can only remember like 7 items at a time or something. It's something like that. Well, if you want to do a human job, but you want it in 500 dimension and 2 million data point, you need a computer. That's why you need a computer to do AI. Okay. Right. So that's it. It's this thing we want to do, but in much higher dimension. So let me tell you the sad news. The sad news is it's not easy to tell this case from that case in 500 dimension. Okay? It's not easy. So, you try both and there's a lot of art, there's a heuristic, there's a trial and error, all kind of stuff. So that's unfortunate. Okay? Now, but there's also an upshot. So first of all, let me get you to your application mindset. If you are trying to market, okay, think of marketing. I'm not a big fan of marketing as a discipline to study, but it's always a good example. It's very easy to think. Okay, so imagine for whatever reason you have 3 populations. How would you use this? Well, first of all, if these were my clients, how many sales representatives would I need to have? I need 3, okay? Because 1 takes care of this one, see what I mean? So this is my client group 1, client group 2, client group 3. I would customize. Now, I think I said this before, and you may have forgotten, so I might as well say it again. What's marketing all about? Number one, you cannot make one product, one service for everybody. You have 2 million customers. You cannot have one solution, one product to sell to 2 million people. On the other hand, you cannot customize 2 million products, 2 million service for 2 million clients. Marketing is always about coming up with a customization vis-a-vis profile. So if you have 2 millions, but 2 millions belong to 3 profile, you make 3 customization, right? And that's manageable. Okay, that's manageable for whatever that is. So think of this as a marketing exercise. Okay, so number one, this is your client. Study them, tell them that's your strategy. So this would be something like your existing client. However, you're not just serving your existing client, right? You are serving new client. Okay, now let me ask you a question. Here comes a new client. Okay, let's say I bring in 5 new clients. Let's make it 5 clients. 1, 2, 3, 4, 5. My question. If I introduce new 5 clients and I were to rerun the algorithm, would my boundary change? Of course, right? Here's the trade-off. If my previous grouping, my clustering is based on 500 people, and I get 5 more people, would it make sense for me to add 5 to the 500 and rerun the algorithm? Probably not. But if I have 500 people, I run the algorithm, I get 300 more. Yeah, it makes sense, right? Okay. So this thing is not static. That's my point. It always reflects your moving population. However, if in the extreme case, I just have 1 more guy, then the problem is no longer a clustering problem, right? Remember, clustering problem is to establish the boundary. But let's imagine that I had just 1 more guy. The question is, with the new guy, what is the clustering? No, the question is, keep the clustering as is. Where should I assign the new guy? So it becomes almost like a classification problem, right? Except the label now is artificially labeled. This is my alpha group, beta group, gamma group. And this guy comes in, I'm going to say, yeah, he's a beta kind of guy. It's like, Slytherin or whatever, selecting the house. Okay. So you can imagine that when this Warthog Academy was starting, they kind of organized young people, and they found out that there are kind of 4 kind of people. So they named this kind of people Slytherin or God knows what. I don't watch that thing. Okay. But once it becomes established, new students come in. Are they going to reorganize the house? No, they use that little hat guy to say, okay, this guy belongs here, this guy belongs there, this guy belongs here. Same thing. Okay. So when you do clustering analysis, you can do clustering analysis once and be done with it. Or you can do the clustering analysis and then build like a classifier. And this is where it gets confusing, right? Last week and the week before that, classifier means I have a real label. Here, I don't have a real label. It's an artificial label called 1, 2, 3. But what's good about it is I can use it for new data. Okay, so I can cluster it once and forget it, or I can quote unquote learn the cluster classifier. That's a different, right? Okay, so if you do it in once and done mode, it's called creating classifier. oh, sorry, creating a cluster, okay? And if new guy come in, you just redo the cluster. It doesn't make sense, but you know, if you have 500 people building the cluster, you have 300 more, yeah, it makes sense. Makes sense, okay? So you can do it in a one-shot deal, or you can learn the cluster classification. In this case, class 1, 2, 3. It's arbitrary. It doesn't mean anything, right? Now, let me tell you what happened. What happened. In real life, this is what I do for my client, okay? The clustering is completely algorithmic, meaning I use the algorithm to do this kind of thing. Once I do it, I try to look at the centroid, and in a way, this here you can also define the sort of centroid, not that great, but in a way you can kind of like find the representation. Instead of giving my client, it's the wrong word to use. My client is a business, so the business has their own client, okay? So my consultancy client is a business. They have 5 million customers. Okay. Instead of telling them that your 5 million customers belong to 3 clusters, cluster A, B, C, or 1, 2, 3, alpha, beta, gamma, what I would try to do is look at individual cluster, try to figure out where they stand. Again, short, fat, tall, and heavy, or whatever. And then I would give it the name. You see what I mean? So in a way, this is what people would try to do in marketing. You know, a term like this is a high net worth client, this is an up and coming new income earner. All these names, okay, basically came from people before computer noticing the group and coming up with the narrative, right? These are the young, aggressive, expensive brand name, crazy people. So we'll call this brand name people, okay? These are the smart young people who invest in their future. So these are the mature young group people, okay? So this is kind of like from their perception. Well, what I do here is before, instead of using the perception of marketing team, I use the algorithm to come up with the clustering. Then look at the salient feature of each cluster. Then you start to give it kind of marketing type name. So if a client could be something like, for example, I would work with clients in fund management. So their client would be something like high earner with no asset. So people with high income, let's say, but haven't bought a house, haven't bought anything or something like that. Or there'll be something like close to retirement. So people in the 50s build a little bit, and maybe they just clean their house debt. So they haven't got any asset either. Oh, sorry, they have got asset, okay? But they haven't got liquid cash either because they just paid their mortgage. So they haven't got much money left, but they have a house, they have car, they have blah, blah, blah. Okay, so this would be one group. So I would call this approaching retirement group, something like that, okay? But the difference between me and the marketing is I did not preconceive the label. That's what data analysts, data scientists do better than marketing analysts. We don't come up with analysis based on predefined label. In this case, in this unsupervised learning. That's the power of unsupervised learning. Okay? Okay. So there are times when working with label, yeah, that's good. That's called supervised learning. This is a time where you really make a difference because you are able to make the distinction based on pure data, not preconceived label. And that's when you become very good or, you know, adding value. So now with that in mind, let's take a 5-minute break. When we come back, bring your, you know, take your textbook out to chapter 5, right? We'll start doing the coding and example.